going.
I've done all of those.
It's a Camino. We got to 10. Right? I think we got to 10 yesterday. I'm starting right now. We got to 10 and pull this out. Now we're at 11 and 12, and if you looked at my answer key for 11 and 12, you saw that these two questions, will vary from person to person because it all depends on what two fractions you picked and whether you're adding or subtracting them. So I can't possibly go over every single scenario. Let me walk you through how to start it, then I'll tell you how to check whether your answer is right without having to have, like me, come check the whole thing. So if you look at numbers 11 and 12 and you read the directions, another thing to make sure that you're reading the directions and you understand what the directions are asking you to find. You can't, tomorrow during the test, raise your hand and say, what's this at? Is this the one that's asking me to do? Like, you can't do that, okay? I'm trying to prep you for college, and basically in college, there's no questions. Unless there's like a mistake or you find something that's, some type of mistake. Professors do not like to be asked questions during the exam. So this is saying find the exact value. Exact means no decimals. This means no decimals. They want your answer in fraction form. And if there is a square root, they want the square root left there. They don't want you actually square rooting it and writing the decimal. Then they do say that you're using the sum and difference identities, which means you need to pull up your formula sheet that you will have. Sum and difference identities right there. It's labeled. Okay? So the directions are telling you what formulas you're using. Right? Looking at the formulas, this should also tell you where we're going with this. Because number 11, let me change to white and come right here. Number 11 says to find sine of 11 pi over 12. Then the directions say use the sum and difference identities, which means go to the sum and difference identities, look at it, clearly looking at which trig function? Sine. So that narrows it down to, okay, I'm right here. Then look at it and ask yourself, what's the goal here? What's the plan? The plan is to take this 11 pi over 12 and rewrite it as either a fraction plus a fraction or a fraction minus a fraction. And the two fractions have to either add to 11 pi over 12 or they have to subtract to 11 pi over 12. And this is where you have free choice. When you are picking your fractions, I tend to go with addition unless it's like some really convenient number and I just see a subtraction route right away. But I tend to think, I don't know why, I tend to have an easier time to add numbers together instead of trying to subtract them off. But it does not matter. The goal, though, is to take 11 pi over 12 and to break it up. I'm going to put big boxes here. All right, to break it up into two fractions that also have 12 in the bottom, right? And of course the pi's right here. So the goal is, what's the number here and here? And are we adding or subtracting? And we want these fractions that we end up with to reduce to fractions that appear on the unit circle, which means we're playing with 6, 4, 3, or 2, right? 6, 4, 3, or 2 are all the possible denominators. So you want to use numbers 6, 4, 3, or 2 with 12, in this case, that were reduced. What do I mean by that? Like, I don't want to pick 10 pi over 12 plus 1 pi over 12. Why do I not want that? Why is, yeah, 10 pi over 12 plus 1 pi over 12 does add to 11 pi over 12, but why will this not work? Pi over 12 does not appear on the unit circle, which means you're still stuck here and you can't go any further. Okay, so you're picking numbers that reduce nicely to fractions that are on the unit circle, because think of it as that calibrating work. You're taking something that we cannot find on the unit circle. I have no clue where 11 pi over 12 is, and we're rewriting it in terms of numbers that are on the unit circle, whether they add or subtract to it. Okay, having said that, I picked, on my example, I picked that instead of 11 pi over 12, I could do 9 pi over 12 plus 2 pi over 12. Because 9 over 12 reduces to 3 pi over 4, which is on the unit circle, and 2 pi over 12 reduces to pi over 6, which is on the unit circle. So those are what I picked. Doesn't matter what you picked, as long as it will add or subtract to give you 11 pi over 12 and will reduce to 2 fractions, radians, that are on the unit circle. Once you get your numbers, you want to reduce them. So 9 pi over 12, this would be 3 pi over 4, and this is pi over 6. And then now you apply that sum and difference identity formula. Mine is the sign addition formula. This is my U, this is my V, right? So I would go through and plug in the U and the V as the formula says. It says sine U cosine V say plus cosine U sine V. Now what you've just done is taken something that we cannot evaluate by the unit circle. You've rewritten it and calibrated it to sine and cosine functions of radian measures that are on the unit circle. So now it's just a matter of looking at your unit circle. Sine means pull which coordinate? Sine means to look at the y. Cosine means look at the x. Now, how am I going to grade this from y'all without having to work every single one of your problems? Easy. Go to your calculator. Pull your calculator up. By the way, I think I told you, I figured out it's my second block class that's taking my calculators. It's not y'all. So if I ever say that, just remind me. All right, I'm going to show you something really nice. This is a safety net for you on this problem. And this is also how I'm going to check your answers to make sure that it's right. The question was evaluate sine of 11 pi over 12, right? Now it says evaluate it exactly, which means no decimals. But the safety net is go ahead and evaluate it with decimals so you know the final answer. You do need to make sure you're in the correct mode. This is what type of measure? It's radian, so you need to be in radian. Just hit mode, make sure radian is highlighted. come out of it, and type it as is. Sine 11 pi over 12. Sine 11 pi over 12. So there's the final answer, which means when you go through the whole process and you get down to the final answer after you plug in the fractions here and then clean it up, you end up with square root 6 minus square root 2 all over 4. Eventually I've run out of room. I can't show you how I got there with that space. But so once you finish it, then type just this fraction in your calculator. Square root 6, come out of it, minus square root 2, come out of it, over 4. Notice that it's the exact same decimal, which it should be. That's how you know you did it right. That's how I'm going to check your answers, because I'm going to look for, first of all, I'm going to look and see if we coincidentally have the same two numbers, and if not, then I'm going to check your answer by typing it in my calculator and seeing if it is the same decimal as what it's supposed to be. Okay? So you should be able to tackle that problem and know you got it right before moving on.
How did you go to after the sign?
Well, next there's a line in between here.
You put it in your calculator.
No, that's where you go to your unit circle. So, let me take a picture. Alright, so you go to your unit circle, and now pull the y value at 3 pi over 4. So right here. So the y value is square root 2 over 2. Can you see? Can you stand by? Can you tell what I'm doing if I just write over it? Alright. And then go now to pi over 6 and pull the x coordinate. So square root 3 over 2. Go back to 3 pi over 4, pull the x coordinate, negative square root 2. Pi over 6, pull the y coordinate. Now you can't type that in your calculator because it's going to take those radicals and change them to decimals, and the directions say no decimals. So you'd have to know how to clean it up. You will get partial credit here for showing me this. I'm looking for this. And then you need to be able to go the next step where you're just multiplying straight across. So that's square root 6 over 4. Multiply straight across. That's a negative times a positive, so I'm actually going to take that plus sign and make it negative. And then this is just square root 2 over 4. And since they have the same denominator, you can write it as one fraction. Now, the tangent one is a little more challenging, and that's because tangent is y over x. So you don't have that nice little go to the radian, pull the x, pull the y. Instead, you have to go to the radian and find tangent by dividing y over x. So if you look at the tan problem, I chose to add 16 plus 3, which reduced to 4 pi over 3 plus pi over 4. Which means if you go to the tangent formula on your paper, why is that not erasing? You go to the tangent formula on your paper, you have this ugly fraction where it's tan of something plus or minus tan of something all over 1 plus or minus tan of each of them multiplied together. So what I always do is I say to myself, okay, I have to know what the tan is. I can't jump straight to the formula. I need to know what tan of 4 pi over 3 is, and I need to know what tan of pi over 4 is. So I go over to the side, and I make a note to myself, okay, I'm going to find it. Tan of pi over 4, tan of 4 pi over 3. Okay, don't complicate something that's not complicated. Type them in your calculator. Like, type it in. You'd be surprised. A couple of them are nice numbers, whether it's 1, -1, 1/2, or -1/2. You have 4 numbers that are nice, and your calculator will calculate it for you. You have 2 numbers that are not nice, and that's square root of 3 over 2 and negative square root of 3 over 2. You actually have more than 4 numbers that are nice. You also have 0. So you have 5. You have 5 possible nice numbers that it could be. Can someone tell me where I'm getting these numbers? Yeah, I'm just pulling them from the unit circle. And then the ugly numbers from the unit circle are these 2, right? Aren't those the only ugly numbers on the unit circle? Oh, square root of 2 over 2. I forgot. You got that one. But what's the nice thing about these 2? When you have tan, it makes -1 or +1. So even though these are ugly, when you're dealing with tan, they end up being nice. So you still, coming back to it, really still only have the 2 ugly numbers. So when you're doing this, just go to your calculator and calculate the tan of those radian measures and see if they are, by some miracle, nice. I can tell you tan of pi over 4 is going to be nice because I know that that's the 45. So there's no need for me to sit here and try to divide y over x, keep, change, flip. No need for that. I can go straight to my calculator and I can find that tan of pi over 4 is 1. Right? Now I've got 4 pi over 3. So type this in. Now this is where it may not be pretty. 4 pi over 3, and it's a decimal. So that tells you that this one has a radical in it. You're going to have to actually find it by hand, keep, change, flip. But the good news is, once you find it, you can check your answer before you go running with it and see if it's right. So 4 pi over 3, you need the coordinates. 4 pi over 3 is right here. So the y coordinate is negative square root 3 over 2. And the x coordinate is negative 1/2. Right? Now how do I deal with that? Keep, change, flip. So you keep that as is. You change it to multiplication. You flip it. And what happens with the 2's? They cancel. Negative times negative is positive, and then you end up with square root of 3. Double check it. What is the square root of 3? It's the same decimal that I got, which tells me I did it right. Now I can run with it. Right? The tangent problem is one of the most common ones where I have to mark and keep going. I'm not looking for you to rationalize the tangent one because it's a conjugate. As long as you get down to, now the way I went, mine ended up like this. And that just bothered me, so that's why on my paper you'll see where I said or, and I just did the cup game with the ones on top. It bothered me to not have them lined up. It doesn't matter. But you could stop here, either one. I'm not looking for you to rationalize the denominator here and keep going. You can if you want, but it's okay. You can stop here. I'm looking for you to clean up any fractions, combine like terms, and just get it as one jumbo fraction as your answer, okay? The only one that has radicals at the bottom is tangent. All right, so that was 11 and 12. 13 through 17. This is that section of question, actually 13 through 16. This is that section of questions where I've warned you that the answers are ugly and it makes you think you're doing it wrong, but you're not doing it wrong. They're just really ugly numbers, really ugly fractions. Everything is straightforward. You do have to draw your picture based on the trig function that they give you, and they tell you what quadrant you're in. So you have to draw your triangle. Remember, your triangle comes from the origin, jutting out and going to the x-axis. They're giving you sine, which means what coordinates? Y over the radius or the hypotenuse. So the y coordinate is 7, the hypotenuse is 25. Now it says sine is negative. Which number is allowed to be negative? The 7 can be. The radius is never negative. Before I can proceed, I do have to do the Pythagorean theorem here to find that x coordinate. If you're bad with negatives, then just use a regular 7 here. I hate to write 7 squared because it's technically wrong because it's negative 7. But this negative is getting squared, and some of you forget to do parentheses in your calculator when you're squaring a negative, and it will spit it out as a negative, and it's not. It's supposed to be positive. So watch your signs there. You end up finding that x is 24, but I'm in quadrant 3, so x is actually, what? Negative 24. So watch that. Then you go to the formulas on your formula sheet that match the trig functions that they're saying to find. They're saying find sine of 2 theta. Well, 2 times anything means you're doubling, right? So these are the double angle identities on your formula sheet. You only have one choice for sine and one choice for tan. Cosine is the one where you have 3 possible formulas. Doesn't matter which one you pick. We will come to the same fraction if you simplified it correctly. And actually, you don't even have to simplify it. You just type it in. So the sine formula is 2 sine theta, cosine theta, and you just plug in sine theta and cosine theta from the picture. The cosine formula that I used was 1 minus 2 sine theta. The reason I use this one, let me show you. Here's a think smarter, not harder tip. Cosine has 3 possible formulas. How am I narrowing the chances of a mistake by using this formula? How am I minimizing the possibility that I've made a mistake by using that formula? There it is. Look at what they gave me. They gave me sine. Well, if I use the formula that is just sine, then I know my fraction I'm plugging in is correct. So there's no way that I've accidentally found the wrong number over here because I'm not using any of the numbers I found. So that's a think smarter, not harder type choice. Tangent, there's only one formula. It's 2 tan theta over 1 minus tan squared. Okay, I'm going to work this one out to show you. The technique would be the same with the previous ones. You go to the picture, you pull the fraction, you plug it in. For tan is opposite over adjacent, or y over x. When I set y over x, I end up with what? What's my fraction for y over x from this picture? Y over X from this triangle be negative 7 over negative 24. What's a negative over a negative? A positive. So when I come right here and write 2 parentheses 7 over 24, do y'all see where that came from? I went ahead and made it positive. Then on the bottom, I've got 1 minus 7 over 24, and this is squared, right? Here's the beauty of this problem. I love this problem because as ugly as it looks, I don't have to do a single thing, right? I can go straight to my calculator and I can type that in exactly how I see it, and it will tell me that really ugly fraction, and that's the answer. So 2 parentheses, this is a way to type a fraction in. You know, parentheses, you just divide the numbers. 1 minus, all right, so look how I have it typed in. And that's the answer. 336 divided by 527. That's it. Now, the next question says, so what quadrant is this double angle in? What quadrant is the double angle in? Well, that means you need to know what the sine of the cosine double angle, and this, when I say sine, I mean S-I-G-N. There's no other word for sine, is there? What value? No. I'm trying not to sound confusing. Is cosine of the double angle positive or negative? There we go. Is what, let's see, our answer came to be what? 527 over 625. And this one ended up being 336 over 625. Okay, so what's the value, like what's the, thank you. No way to say it without saying sine. Now looking at sine of the double angle, is it positive or negative? Look up there. It's positive. So if the cosine's positive and the sine's positive, then I'm in what quadrant? 1. Now the 17 is the half angle. Go to your formula sheet, pull the formula for tan of the half angle. I pulled the one that does not involve a square root. I pulled the one that doesn't involve a square root, which is why my answer doesn't have that square root anywhere in my work. I pulled 1 minus cosine over sine. And now it's, you're plugging it in. Same picture. That's why this question is tacked into the end of this. It's the same picture. So cosine is negative 24 over 25. And sine is what they gave me, negative 7 over 25. And then I type that in my calculator. Exactly how it looks. And I got negative 7. All right, we have 8 problems to look at. We have 8 problems to look at, and I would say these are probably, the first 4 are the hardest. The last 4 are probably easier because they're the proving. They're the manipulate one side to get to the other side, right? Let's jump around. Let's jump to the last 4, since they are, when I say easier, I just mean you have that direction, like you know where you're trying to get to. Prove means manipulate one side to match the other, or manipulate both sides to match each other at some point. I manipulated both sides on number 22. and then I manipulated just the left-hand side on the last three. It's a guess, it's a puzzle. It's just a guess and check. 22 though, both look ugly to me. Like the left side has that square and then the half angle, so I knew, okay, I gotta get the half angle to a regular angle. So I knew I had to change that. And then the right side just has the tan, and then there's a tan on the bottom. I know that's a fraction with another fraction. So I could already see, like, okay, I'm going to have a common denominator, keep, change, flip coming along. So now the others, like to me, this is an obvious only work on the left because the right-hand side's just 1 over sine. So that's, and then down here, did that work? Yeah, down here, this one is so ugly. We have never taken that and manipulated it. We've never taken something that ugly and extends to the 4th power and all that. We've never done that. So this was my clue. Looking at this right here, that says 4 times the angle. I know that that needs to be adjusted to just plain X, which is, notice every single one of these is plain X. You see that? So that tells me, okay, manipulate the left because I'm going to end up with that right-hand side. All right, so number 22 is actually not as bad as it first starts out. That looks hideous. So I immediately said, okay, I need to work with the left-hand side because I don't even know what I'm looking at when you have that half angle identity in there. Go to the formula sheet. Half angle identity for, is it cosine? Yeah, cosine. Okay, there it is. It's right here. The plus or minus doesn't play a role here because we don't know what quadrant we're in. We don't know anything about the angle. So that's just irrelevant. That's for when you're evaluating. We're not evaluating. We're just trying to prove the identity. So ignore the plus or minus. I copied the entire square root. 1 plus cosine x over 2. So this is the half angle being squared. So I copied the half angle, which we said was the square root of 1 plus cosine x over 2, and it's being what? Squared. So I'm going to put parentheses around the whole thing and write that it's being squared. And immediately I can see, okay, this actually ends up being nice because what happens when you square a square root? They cancel. So now that ugly mess is actually just 1 plus cosine x over 2. And then I felt like, okay, that's not bad. That's pretty. Now I'm going to go to the right-hand side and play with the right-hand side. And when you do that, I'm not going to work the whole thing out because y'all can see my answer key. The right-hand side, tan x plus sine x over 2 tan x. I know immediately that I need to take tan and rewrite it as sine over cosine. And I need to be careful here because now I have a fraction inside of a fraction. Right? Notice the way I wrote sine x, the one that's just plain sine x. Notice that I wrote it bumped up so it's level with the sine x from the tan. So that's to remind me that I have an understood 1 right here. Remember when we were doing this, I said the goal, if you have a fraction within a fraction, you always need to get it to where it is simply a single fraction over another fraction before you can keep, change, flip. I can't keep, change, flip here yet because of this plus sign crap. So I've got to get a common denominator in the top. Just ignore the bottom, focus on the top. So you could take your pencil and say to yourself, okay, so really the problem is the sign. This needs to be multiplied by cosine over cosine, right? And now I can see where I can combine the top fractions. Which is where, if you look at my work, you can see where I went with that. Then if you look at the next line, you saw where I pulled a sine out that they both had, and I got left with 1 plus cosine, which was the goal, and then on the bottom you end up with 2. Does anyone have any questions on finishing 22? Look at my answer key. Do you understand it? I factored, you see right here, focus on just right here. When I go and combine that fraction, I notice they both have a sign. I also know that my end result there needs to be no sign at all. So that told me, okay, they both have a sign. What if I pull the sign to the front, factor it out? It's the equivalent of having, like, if you had this. They both have a y, so pull a y to the front, you'd be left with 1 plus x. So I get left with 1 plus cosine. And when you keep change flip, the signs cancel. So this ends up being sine x plus sine x cosine x over cosine all over 2 sine cosine. Now I have a fraction divided by a fraction, which means I can keep, change, and flip it. So keep, change, flip, then I can see that cosine cancels. And you don't have to factor the sign to the front, as long as every single term, if you recognize every term has the sign, you could say, okay, that sign's going to come out of every term up here. Watch your terms. Watch your terms. The only way to cancel something is if every term can cancel it out. So that plus sign there means you have 2 terms. So they both have to have that sin x for it to cancel out. And you also have to be careful when you cancel that you remember right here was something. It doesn't just disappear. Now I did a sine divided by a sine, so what does that become?
1.
A 1. This becomes 1. Which is why the answer is 1 plus cosine x over 2.
How do you still have a 2?
Right here.
But isn't it canceling out because of the sign?
No, 2. This 2 is a product. It's multiplying.
So how were you able to cancel all those signs then?
This 2 has nothing to do with that sign. It'd be like me saying cosine x over sine x, right? Times 1/2.
Yeah, but I'm just saying, how did you cancel out both the signs then?
Because it's a 1 for 1. The 2 has nothing to do with the sign. It's not sine squared.
No, I thought they would match, so it's like 1 for 1. Yeah. So.
Right. This is a multiplication in front of it. Okay, look. Go back to letters. Go back to letters, y'all. Nothing wrong with taking letters. X's cancel. There's a y here that comes out of those. And I'm left with 1 plus x over 2.
So if there's 3 y's on top of the first fraction, if you put like another y plus y plus yx, I could cancel all 3 of those y's.
But still have the 2 left over.
Where'd you put another y?
I just put it at the side. Like put that one Y at the bottom. All three.
Yeah, because it's a factor. The 2 is not the factor.
So it doesn't matter how many there are, it's Y.
Do y'all remember prime factorization tree? 8 is 2 times 2 times 2. Right? It's just a single factor that they have in common. It's the y. They don't have a 2 in common. The 2 doesn't have anything to do with the y right here because it's.
I think we get, like, there's nothing to do with the 2, but how are you able to cancel both sides if you have one sign? Like, how is the sign able to cancel all
So
of the
that's
signs?
why if you look at my answer key, I'd hit clear, but then it's going to erase all my work. If you look at my answer key, right here, I took this and I rewrote it as this. They have a common factor of sign. If you look at my answer key, you're going to see where I pulled that common factor out to the front, which would leave, if you imagine dividing by sign, 1 plus cosine would be left. And now you can see that sign is only taking it. Some people can cancel without factoring a GCF out, and then some people need to see the GCF to be able to cancel, which it sounds like is where you were trying to understand how it was canceling. So pull it out as a GCF, and then you can see why the 2 gets left.
I got that, but we usually just do it like once on one.
Well, the what I tend to do is pull the GCF because when I go in and try to cancel while it's within its terms, I have people start canceling flippantly. Like if we had, say it was 1 plus sine x, cosine x, yada, yada, yada. And then over here on the bottom you had that 2 sine x. I get nervous canceling when it's in the format of the green because I've seen people say, oh, there's a sign, take it out. You can't do that because of this right here. There's a term here, and I'm making it really big because it's the giant 1. Like you have a giant 1 there that you can't take this sign from this term because it's attached by addition to the 1. So that's where I get nervous canceling it out when it's in plus and minus form. I like to pull the GCF out because then they can see that it cancels. If you look at number 24, 24 is that question in the notes. I don't remember what day, 7-2 maybe? And I said, I think the one in the notes said sine 3x. It was at the bottom of one of the notes packets, and it was, I think it might have been sine 3x. And I said, there is one of these on the test. One of them. And here it is. So you have 4x. We can't evaluate 4x. We need to get it to terms that we can evaluate. We can only evaluate single x, double x, or half angle, right? Lord knows we don't want a half angle. So how can I rewrite 4 in terms that I can evaluate? Do I want to do 1 plus 3? I don't want to do 1 plus 3 because I can't evaluate 3x, right? I want to do 2 plus 2. So I'm going to take the left-hand side, cosine 4x, and I'm going to rewrite that as cosine 2x plus 2x because I have double angle formulas. And then now you're going to take your Q, number 10 and numbers 11 and 12 should help you here. 10 is where you're just wide open on your own. This one is saying, hey, by the way, this is the answer you're going to come to if you'll do this correctly. So this is exactly like number 10, but I'm telling you what to get to, okay? So you're going to separate this as the cosine double angle formula using the sum and difference identities. When you have cosine of addition, it becomes cosine double angle minus sine double angle. What is this right here? If you have cosine of something times cosine of something, that's actually just cosine squared, as long as the somethings match, right? You see how these match? Double, 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 double. So this is actually just the square of the double angle and the square here of the double angle. Then you go to your formula sheet and you can use substitution here for the double angle. For cosine, now there's possible routes here. You should come to the same answer though once you clean it up. For cosine, I picked cosine squared minus sine squared. For sine, you don't have a choice. You have to pick, you have to do 2 sine cosine. So this becomes cosine squared of the single angle minus sine squared of the single angle. Don't forget though, the whole thing was what? Squared, right? These squareds here have nothing to do with that squared there. These squareds come from the formula. That's the formula for the double angle of cosine. This squared right here is because it's squared. So then it's sine, and it's also squared. Be careful. This means squared. Now you have to multiply that out. You have to be careful. That is a binomial times a binomial right here. I would recommend multiplying that out with just letters so you don't mess up. Maybe, come over here and say to yourself, so that's x squared minus y squared, and I'm squaring that. So that's multiplying it by itself twice. First, outer, inner, last. So x to the 4th minus 2x squared y squared plus y to the 4th. Now you can see these are coming in. Look at that. It's coming together. That's x to the 4th. There's a cosine to the 4th. That's positive y to the 4th. There's a plus sign to the 4th. This squared right here means you're squaring every single thing in there because you're multiplying it times itself, right? It's just a single term times itself. So if you need to imagine that, I'm going to draw an arrow. That's 2 sine x cosine x times 2 sine x cosine x. So that's where you get 4 sine squared cosine squared, which is on the verge of my answer. I'm getting there, closer and closer. So then you would plug that back in. Now you can see right here, this is positive 4. Or actually, there's a minus sign right there. So this ends up being minus. You see right here and here? Those are the same format. This is negative 2 cosine squared sine squared. This is negative 4 sine squared cosine squared. It doesn't matter the order there. So that's where the negative 6 comes in. Jumping to 18 through 21. 18 through 21. Number 20. Right here, because this is cosine of a double angle, there are 3 possible routes for you to go. And on my answer key, I did all three. I worked all three so that you could see, depending on which way you go, like what you should get. Remember though, this is, no, this is just simplifying. So your answer, depending on the route you went, may be different than your neighbor if they went a different route. But all three of my possible routes are answered on here completely. Remember the simplifying and proving questions, meaning 1 through 7 and 18 through 25. 1 through 7 and 18 through 25. Those types of questions on the test will be questions that we have done, whether it was in the review, whether it was in the homework. Don't forget that printed homework from 7-3. Remember I gave that to y'all? I didn't take a grade on it because I was like, you know, we're gonna go on the faith-based system, honor system. You were supposed to try the homework on 7-3 to print out, and then I posted the solutions on Tuesday. They're posted under the 7-3, not tab, subject, whatever. But the ones that cover these types of questions will come from questions we've done. So I'm not throwing a new one at you. Okay, it's my point. If you've done everything we're supposed to do, I'm not throwing a new one at you, which I hope brings a little bit of relief that you're not expected to do a new one.
So is it gonna just be 1 through 7, 18 through 25? Like those questions are gonna be on the exam block. So from 7 to 18, the other ones aren't gonna go in there. So don't focus on those.
No. What I'm saying is the remaining questions are the same type. I'm asking those types of questions, but I'm not putting on the test find sine of 11 power of 12. I might put find sine of 8 pi over 3. So it's the same concept. What I'm saying is these types of questions where you have that free choice to go because it's simplifying and proving. I'm not going to give you a new one. I'm going to give you one we've already seen and done.